Hello, looking at Unit 12. Really kind of starting our circles unit. There's lots of things that we know and love about circles, and we can do a lot of things. Today we're going to focus on sort of tangent lines and properties of tangents. So just to review, as our parts of our circle, we've got the center. From the center to the edge of the circle is a radius. And then from one end through the center to the other end is the diameter. A chord is it still goes from like our one spot on our circle to the other, but it doesn't go through the center. So it doesn't necessarily have to go through the center. And it's kind of like in addition to that, we've got something called a secant line. So where a chord stops at the circle, a secant line keeps going, and it touches our circle at two different places. Touches it here and here. Now, a special type of secant line, again, is if I just keep drawing them, I keep drawing them, I keep drawing them. Eventually, I'm going to get a special secant line that just touches my circle once, right on the edge of my circle, and we're going to call that line that creates that one touch a tangent line. And where it touches is called the point of tangency. So a tangent line touches your circle exactly one time. Tell how many common tangents the circles have and draw them. Okay, so if I look at this, so again, tangent lines, a line that can touch it twice. I could draw a circle here and here. That would be one tangent line. Again, because it's shared, it's common. And similarly, I'd have something like this. Let's see if I can draw this. Oops. Lost it. There it is. Two so far. I also have some in the middle here where I could say, all right, something like this could be a tangent line, and basically the same thing over here. So these sets of circles actually have four common tangent lines. These circles, again, kind of the similar idea on the top. I see that I've got one right here on the bottom. Same idea. I've got two. Oh, that's not very good drawing. Let's see if I can do a better job. It's more something like that. Again, it's not 100% because it's by hand. And there's actually a third one right in the middle here, where if we were to draw, again, if these circles only touch at that one spot, we could draw a line through there. And this last one, I believe, is only going to have two points of tangency. 1, 2. So this one had 3, and this one had 2. How do we know if a line is tangent to a circle? Well, one of the big things, or one of the key ideas, is that a tangent line will create a right angle. It's going to be perpendicular. So again, perpendicular means it meets at a right angle. And that's going to be really useful for us as we work through problems and try to solve them. So let's kind of jump into an example, but it works both ways. So if I know that it's 90 degrees here, then I know that it's tangent. Or if the directions tell me it's tangent, well, then I know that it equals 90 degrees. In the diagram, PT is a radius of P, is ST tangent to P. So if it's tangent to P, then we know that we have a 90-degree angle here. And if I know that I have a 90-degree angle, well, then I can try to do the Pythagorean theorem. And I could say, all right, I'm going to take my leg and my hypotenuse and my other leg. And I'm going to say leg squared plus leg squared equals hypotenuse squared. 12 squared is 144. 35 squared is 1,225. And 37 squared is 1,369. And when I add these up, I end up getting the same exact thing. So because this is Pythagorean theorem is true, we proved that this is a right angle. So yes, ST is tangent to circle P. And that's how you'd read this statement. See if I can draw it more in the center. Come on. There it goes. ST is tangent to P. Let's take a look here. In the diagram, B is a point of tangency. Find the radius R of circle C. So I know, again, in the directions this time, it tells me that B is tangent. So again, if I were to set this up, I would say, okay, using Pythagorean's theorem, I've got leg, and then across from 90 is my hypotenuse. So I'm going to set that up as R squared plus 80 squared equals, and how I'm going to write this is 50 plus R. Again, leg small plus my small leg equals my, or small piece plus small piece equals big piece. So as we were to write this, R plus 50 squared, we FOIL it out. Again, taking R times R, R50, here, and we simplify it and end up getting R squared plus 100R plus 250. So I'm going to plug that in, and again, as I work through and simplify, I say, what's the first thing I'm going to do? I'm going to subtract R squared, so it cancels out. All that I'm left with as I simplify is 6,400 equals 100R. I'm going to subtract on both sides and then divide by 100 to get a radius of 39. One other sort of additional use or property that we have here is that a tangent segment can come from an external point outside like this. And this is going to tell us that this line ST is congruent to this line SR. So if we have this external point out here and I know ST, well, I actually also know SR as well. So if I look at this example, RS is tangent to circle C at S and RT is tangent to circle C at T. Find the value of X. Because this line is, congruent to this line, I'm going to set them equal to each other. And this becomes a relatively simple algebra problem. Not 12, let's say that's 8. X equals 8. More examples. Is DE tangent to circle C? Again, if it's tangent, then this has to be a right angle. Okay, has to be a right angle. If it is, then I can set up Pythagorean's theorem. So over here is my hypotenuse. This is my leg. This is my leg. And I set it up, again, I set it up as leg squared plus leg squared equals hypotenuse squared. And one leg is 3 and one leg is 4. My hypotenuse, I'm not quite sure. It says this area here, this part's 2. Okay, I know this part, but I don't know that what this green part is right here. Except this is the center to the edge of the circle, which is my radius. And over here, the radius is 3. And we know that the radius is always the same inside of the same circle. So really, 3 plus 2, my hypotenuse is going to be 5. 3 squared is 9. 4 squared is 16 equals 25. 25 equals 25. Cha-ching. So, yes, it is tangent. Find the values of s of x. So if we think back to the theorem here, okay, we have one way to tell that these lines are tangent is that they are congruent, which again, we remember if it's tangent, it's got to cross at a 90-degree line, okay? So as I look back at this example, because it tells me that it's 90 degrees right here and it's 90 degrees right here, I know that these two lines are going to be congruent because it's basically the same property, and I can set them equal to each other. And when I take x, I get 3 positive or negative. So again, because it said values, x could be positive 3. 3 times 3 is 9. X could be negative 3. 3 times negative 3 still equals positive 9. Directions tell me, yes, it is tangent, okay? Because it tells me that, I know a lot of things. I can say, all right, we already did one somewhat like this. It must be 90 degrees. If it's 90 degrees, I can use Pythagorean's theorem, leg, hypotenuse, r squared plus 24 squared equals. This is where I come into a little bit of problem. I don't necessarily know what this is called. We're going to call this r plus 18. But because our formula requires us to square it, we're going to do that work on the side here. R plus 18. When I multiply, FOIL technique, I get r squared plus 18r plus 18r plus 18 times 18 is 324. So I'm going to be left with r squared plus, I got to combine like terms, 36r plus 324. Ran out of room there. See if I can fix that. All right. And so we're going to plug that in over here. What we just solved. Plug this in right here and say this is going to equal r squared plus 36r plus 324. 24 squared is 576. So r squared plus 576 equals r squared plus 36r plus 324. Switch colors so we can see. I'm going to subtract r squared, that cancels out. I'm going to subtract 324, and get 252 equals 36r. And the last thing to do is divide by 36 and get r equals 7. So that was a lot of work to find the radius, but the radius is 7.